Quantum mechanics challenges our everyday understanding of reality by suggesting that even large objects can exhibit wave-like behavior, a concept that sounds almost unbelievable when applied to the macroscopic world we interact with daily. But here's where it gets controversial. Can the strange rules of quantum physics truly describe the behavior of objects we can see and touch? Or is there a fundamental limit where classical physics takes over? This question lies at the heart of ongoing research that aims to blur the line between the quantum and classical worlds, potentially unlocking new ways to test the foundations of physics and develop advanced technologies, such as ultra-sensitive gravitational sensors. A groundbreaking study by scientists from ETH Zürich in Switzerland and the Institute of Photonic Sciences in Barcelona, Spain, has made significant progress in this quest. They have successfully extended the quantum wave nature to nanoparticles, tiny particles about 1,000 times larger than individual atoms, pushing the boundaries of quantum mechanics into a realm previously thought to be dominated by classical physics. Quantum theory predicts that all matter, regardless of size, should exhibit wave-like properties. However, for larger objects, this wave behavior is confined to an extremely small spatial region called the coherence length, which is typically much smaller than the object itself. This tiny coherence length makes quantum effects practically invisible in everyday objects. As lead researcher Massimiliano Rossi explains, to bring quantum physics into the macroscopic world, we must simultaneously increase both the mass of the object and its coherence length. This dual challenge motivated their recent experiments, detailed in the journal Physical Review Letters. The team focused on silica nanoparticles roughly 100 nanometers in diameter, about 1,000 times larger than atoms but still incredibly small. These particles were tracked and levitated in a vacuum using a highly focused laser beam, a technique that isolates them from environmental disturbances. When the laser light hits the nanoparticles, it scatters, and the phase of the scattered photons carries precise information about the particle's center of mass position. By feeding this information back into the system, the researchers applied electric fields to cool the nanoparticles close to their quantum ground state. Cooling is crucial because a colder particle occupies a purer quantum state, allowing its wave-like nature to extend over a larger spatial region, effectively increasing the coherence length. Initially, they measured a coherence length of 21 picometers, 21 times 10 to the power of minus 12 meters. To push this boundary further, the researchers cleverly manipulated the laser light. They began with a high-power laser that created a strong harmonic potential. Imagine a marble resting at the bottom of a steep bowl, tightly confined. The beauty of using light to trap particles is that the steepness of this bowl can be finely tuned by adjusting the laser's power. By gradually lowering the laser power in 2 distinct pulses, the bowl became shallower, allowing the marble, the nanoparticle, to move more freely and explore a larger area. This process translated into an impressive increase in the coherence length to 73 picometers, more than 3 times the initial value. However, maintaining quantum coherence is no easy feat. Rossi highlights that the biggest experimental hurdle was minimizing decoherence, the process by which quantum information is lost due to interactions with the environment. When a nanoparticle interacts with its surroundings, it becomes entangled with a complex, noisy environment, causing its motion to appear random and classical rather than quantum. This loss of quantum behavior is why macroscopic objects usually don't display wave-like properties. To succeed, the team had to expand the coherence length faster than decoherence could destroy it. They meticulously identified and suppressed all sources of decoherence, with laser light scattering being the primary culprit. Fortunately, during the laser power reduction pulses, scattering was naturally reduced, helping preserve the quantum state. While the achieved coherence length of 73 picometers is still minuscule compared to the nanoparticle's 100 nanometer size, Rossi points out that there is no known fundamental barrier preventing coherence lengths from reaching the nanometer scale. This opens exciting possibilities for future experiments, such as applying additional expansion pulses to further increase coherence. Looking ahead, extending the coherence length over longer times will require even more sophisticated techniques to outpace decoherence. One promising approach involves hybrid traps that combine light and electric fields to confine nanoparticles. Electric traps could significantly reduce decoherence caused by light scattering, offering a cleaner environment for quantum behavior to flourish. Rossi is actively exploring this avenue with his new research group at Delft University of Technology in the Netherlands. This research not only pushes the limits of quantum mechanics, but also raises intriguing questions. How far can we extend quantum behavior into the macroscopic world? Could future technologies harness these effects for practical applications? Or will classical physics always dominate at larger scales? And importantly, what does this mean for our fundamental understanding of reality? We invite you to share your thoughts. Do you believe quantum mechanics can fully describe the world we see? Or is there a hidden boundary yet to be discovered?